Hi, this lesson is on 2.2, Newton's second law. So first we'll start by recalling Newton's first law, the law of inertia. That one is stated by saying any object in motion wants to stay in motion. An object at rest wants to stay at rest unless acted upon by a net force. Newton's second law takes a look at what net force is equal to. So any net force produces an acceleration in the direction of the force. The magnitude of the acceleration is directly proportional to the force and inversely proportional to the mass. So it's a rather simple equation if you look at it. F equals ma. We use this in Science 10. We'll continue to use it here, but this terminology that they're using in the actual definition is more of the Physics 20 application. So we'll take a look at what directly proportional and inversely proportional actually means. Directly proportional means if one thing increases, the other thing will increase. So in this example, if force increases, mass remains constant, that would mean that acceleration increases. And you can do a really basic example to see this. So you can take any ball that you have at home and you can apply a force to it right now in your living room and it will accelerate. So if I take my dog's chew toy and I apply a force to it, it's going to accelerate across the room. Now, if I use the same chew toy, so mass is constant, and I increase the force that I've applied to it, so I push it harder, what's going to happen to the speed of the ball? Of course, that acceleration is going to go faster. So directly proportional means if one thing goes up, another goes up, or vice versa. Indirectly proportional means as we increase the mass, the acceleration would decrease. So increase, decrease. The opposite's happening, whereas directly proportional means the same thing is happening. So in this one, we're assuming that the force is constant. So take that same example. I'm pushing a tennis ball across the room. I'm using the same force both times. Now, if I change the tennis ball to a bowling ball, the mass has increased. That's a much heavier ball. What's going to happen if I still push the same force that I used before on the tennis ball on the bowling ball? The acceleration will decrease. That's what indirectly proportional means. Here's some examples with the formula. You can see that the math is very simple. We've got force equals mass times acceleration. Something to note, force is a vector, so force has direction. Joe has a mass of 100 kilograms. What force is needed to accelerate Joe to 1.5 meters per second squared? So in this one, we've got force equals ma. We've got the mass, we've got the acceleration. Ideally, we would write our work properly with units. We times these, we get 150 newtons. That is the unit that we apply to force. And ideally, I would go one step further here and use proper sig digs. I'd say 1.5 times 10 to the 2 newtons. A spring scale can pull with a force of 2 newtons. What's the maximum acceleration such a scale could give to a 3.5 kilogram object? This is where we have F, we have M, and we want to solve for A. So if you're practicing rearranging formulas initially, divide both sides by M. So acceleration is force over mass. Here you can see that division. Put your units in here. I forgot to do that. And then your acceleration will be 0.57 meters per second squared. As an extra challenge, I'd like you to analyze the units here. Now, newtons are what we use for force, but you can see that acceleration didn't end up being newtons over kilogram, like you would see from the formula if I had them in there. So newtons actually come from all of these base units that we use. So the base units are kilograms, meters, and seconds. So see if you can, before we move on, pause the video and figure out what the base units or the fundamental units, as we call them, for force would be. All right, if you tried that challenge that I gave you, you would find that newtons are kilograms times meters per second squared. This comes from the fact that F, force, equals mass times acceleration. So you can see the unit for mass there, multiplying by the unit for acceleration, meter per second squared. So when we're talking about newtons, this is just really hard to work with. There's a lot going on in this unit. We gave Newton the credit that he deserves. He discovered 3 laws that still make sense to this day. So we, instead of using the fundamental units, usually say newtons. Now, a person's mass is 88.18 kilograms. What is their weight? So keep in mind, usually in everyday English, we use the term weight incorrectly. We're really referring to a person's mass. So weight is equal to a person's mass times acceleration due to gravity. I would usually write this just as the F equals ma formula. Force equals mass times acceleration. When you're talking about weight, acceleration is acceleration due to gravity. On Earth, 9.81 meters per second squared. Now, if you write weight as force, I think it makes more sense. Your weight is actually the force of gravity. So what you will see me write in the textbook and other places is F subscript G. I'm sorry I can't write that on the notes with this program, but Fg is something that you can call weight. You will see textbooks write a lowercase w with a vector arrow, but Fg is my preferred way of writing it. So the mass, kilograms, acceleration due to gravity, multiply them out, sig dig your way through this. Remember G, you don't count sig digs because this is a constant that we're using. So 4 sig digs. And since it's a force due to gravity, that's what weight really is, we use the units newtons. Now questions on page 149, 1 and 2. Example 3.6 on 150 and the practice problems in the yellow box next to them. And this is a typo, example 3.8 on 152 and the 2 practice problems that it has. Let me know if you need any help or have any questions.